This morning I will share with you data I gathered on an antenna performance experiment using WSPR, the weak signal propagation reporting software. I conducted this experiment on an HCLW-20 antenna, and now before you guys go start looking up and Googling what an HCL20 antenna is, you need to know that as an engineer I have to name and serialize everything I make. It's what we do. So the HCLW-20 stands for the highly compromised long wire antenna that I installed at my QTH in 2020. I received my general class license in 2019 and due to HOA regulations installed a 40-meter dipole in my attic. Unfortunately, the attic was covered with Tech Shield, which is an aluminum heat barrier lining that lines the entire inside of the roof. It became very obvious to me that my propagation was compromised, so I decided to fool the Homeowners Association and install a long wire antenna. And this is the story of experimenting using WSPR on that newly installed long wire antenna. For those of you who are not familiar with WSPR or WSPR, it's a digital mode developed by Joe Taylor, K1JT, who won the Nobel Prize in Physics. He holds a PhD in disciplines of physics, astronomy, and applied mathematics, and is the author of the WSJT software package for long-distance, low-power, weak-signal communications. This package includes things like WSPR, FT8, JT65, and other modes. This is an open-source software. WSPR is an open-source software, and sometimes you'll find it embedded in other software applications. Just a little bit about setting up WSPR. It is a digital mode, so you'll need a computer. WSPR runs on Windows, Linux, or Mac, and you need a sound card or an external interface modem to your computer. With a lot of many newer transceivers, they have direct USB ports, so you just hook your SDR transceiver right up to your computer. The transmission for WSPR is 50 bits. And it's a compressed, encoded bit stream with forward error correction. So there's a total of 162 bits in the transmission, which includes the 50 bits information and the forward error correction. It uses a frequency shift key, FSK, at 1.4648 baud, taking up a bandwidth of about 6 hertz, so it's really efficient. Each transmission runs 110.6 seconds, and in that transmission you have the exchange along with the forward error correction. The exchange is your call sign, or in the case of receiving, the transmission call sign, the locator of that transmission site, in Maidenhead grid, and the transmitting power that the transmitter is transmitting on in dBm. The transmission happens in 2-minute intervals starting at 1 second into an even UTC minute. And again, that lasts for 110 seconds. So there is some small amount of downtime for decoding and other purposes. The WSJT software allows you to set the number of transmissions as a percent of the intervals. So as an example, if you go 100 intervals of transmission and you set the percentage of your own transmissions as 10%, you would be transmitting 1 out of every 10 intervals. Receiving and decoding WSPR signals provides the spots that you have received or the spots that have received your transmission. That happens in the user interface. These are also uploaded to a database called WSPRnet, which basically is a central database of all WSPR activity. The users can choose to upload or not upload that information, but I do find that a lot of information exists in there, and most people do upload. Several websites provide analysis and mapping functions using WSPRnet. I'm going to demonstrate one to you called WSPR.rocks. All right, now I'm going to show you a quick demonstration of the WSPR software, and I am using the WSJT-X version that contains WSPR. WSJT-X is a software package by K1JT that includes multiple modes, including WSPR. So you'll see here that it includes FT8, JT65, as well as other modes and Whisper. And I have Whisper selected here. So if we have Whisper selected, which we can verify at the lower part of the interface here, we will be monitoring the selected frequency. And right now I have 40 meters selected. And as you can see, there are help contexts as you put your cursor over top of different areas of the screen. It'll tell you what that is. So we're currently monitoring 40 meters. Down here at the bottom of the user interface, you will see that there is a timer. This is the 2-minute interval timer, and we're getting towards the end of the interval. So you'll see that we've just started decoding, which it does automatically, and now it lists in the user interface the spots that we have seen in the decode. And in that, you see all of the data that came from each of those transmissions. So we see what the signal-to-noise ratio is, which is calculated by the software. We see what the frequency is that they were transmitting on, if there was any drift in that transmission, and then the information that was actually transmitted by the call. So this was the call letters transmitted, what grid they were on, and what their power level is. And you can see everybody is below 40 dBm or below 10 watts. So again, most people are using a very small amount of power when they're using Whisper. And then the software uses the Maidenhead grid and your Maidenhead grid that you have listed in the preferences to determine what the mileage is. And that can be either in miles or kilometers. So you can see here that we're basically on 40 meters, and this is the middle of the day. It's currently about 4 p.m., 4:15 p.m., and we are seeing only North America on 40 meters. Speaking of time, I do have my ham Macintosh running at UTC, so you can see these are UTC times, and it's also listed here in the user interface what day and what the time is. So all of this information was monitored and decoded, and I have it selected to upload. You can see right here there's a selection where it says to upload spots. This uploads all of the decoded spots up to the WhisperNet database. So that database has now got all this information, and I'll be able to pull from that and look at different statistical data, which I'll show you soon. So we are now decoding another 2-minute interval, and you'll see that the information comes up. I'm going to move this now to 20 meters, and we will start decoding at 20 meters, and we'll see that come up here pretty soon. Some other elements of the user interface here include a meter that shows you what the signal level is coming from the selected Whisper part of the band. And down here there is a waterfall where you can see if you're receiving anything. And we can see, you can barely see there's a little green line here, which is the active part of the band for Whisper. And then there's a red area that shows where my transmission is selected. So if I was transmitting, I would be transmitting at 1406. And you can change that right here with this particular input. So I can select that up or down and move where my transmission spot is. This allows me to select a spot in the band where no one's participating right now in Whisper, so that I don't step over somebody else that might be close by. I talked about in the earlier part of the presentation that you can select how many times you transmit in the 2-minute sequences, and that's selected here. So with 15% selected, I would be transmitting 15 times out of every 100 2-minute intervals. So that allows me to select how many times I want to transmit versus how many times I want to receive. There's also the ability to do band hopping, which will automatically sequence between bands. If I select that and then look at the schedule, you can see that I can select which bands that I might want to monitor or transmit on and what times a day. So I can select any basically grid here of whether I want to receive only from that part of the band, whether I want to transmit and receive, or what time of day. It also allows me to retune my antenna as it switches between bands. So you can set this up very well to automatically look at a wide range of bands. So we've ended another 2-minute interval, and now we were monitoring 20 meters, so we can see the 20-meter spots that have been listed here, and those are now all uploaded as well to the WSPR.net database. There's also a power level controller here. This basically controls the audio output levels from your computer to your transceiver. And you want to make sure you set that just at the point where your transceiver's automatic level controller starts kicking in. So when you're setting up WSPR and you're transmitting, you want to adjust that power so that the ALC just starts to kick in, and then you want to pull it back just a little bit. You do not want the ALC kicking in because it will fold over or clip some of the audio transmissions. So there we go. That's the interface for WSPR, and now we'll take a look at the WSPR database. Okay, now we're going to move over to the web browser and look at the WSPR.net data that has been uploaded from the software that decoded those WSPR transmissions. And I'm going to use a website. That's WSPR.rocks. And this is basically a website that provides a user interface into the WSPR.net data. And there are several different ones of these. I like this one because it just has a little nicer reporting on the maps, which is one of the features that I like using the most. So first, let's get a search in the database. I'm going to set my search parameters for the time is the first selection, and I'm going to choose the last hour. I'm going to go ahead and leave it on all bands, but if I wanted to, I could only search the 20-meter spots or the 40-meter spots we have, but we'll look at all of them. And we'll find more than just the 20 or 40-meter spots because I left the software running after we were finished with the demo, and I left it with the schedule turned on. So it's band hopping now between 40, 30, 20, 17, and 15. So we'll see some other spots now that we didn't see in the demo. I'm going to set the transmit or the receive call to my call sign, which is KN4RHI, and I'll leave the transmit call to everyone. So basically, we are going to look at how many spots were uploaded in the last hour on all bands from the KN4RHI WSPR software, which is what I was running during the demo. And we're going to look at any call sign. I'm not going to worry about unique calls right now, so some of them will be doubled up. We'll have multiples from certain call signs that were seen during multiple passes of the decoding intervals. And we're not going to worry about max spots. If you run this thing for many days, like I did in my experiment, I did a 7-day data collection. And you'll get thousands upon thousands, not tens of thousands of spots. And so this gives you a way of just limiting how many you search for. I'll come back to auto search here in a second. So we're going to go ahead and search this on the map. So search this. And so this is the report we get from the database. It gives us the timestamp when the reception occurred, the transmit site, the transmit grid, the receive grid, the receive call sign, and the receive grid. What frequency was it on? And you can see that we've got some here in 15 and 17, which we didn't do in the demo. But like I said, it's continued to run since the demo was on. It gives me the amount of power from the transmit site. You can see a lot of them are very low, 0.2, 0.2, but occasionally you'll see something around 20. It's not unusual to see somebody up in 20. The signal to noise ratio that was reported, any drift that was calculated in the decoding, how many kilometers it is from the transmit site to the receive site. So this is the amount of distance in kilometers from the transmit grid reported to the receive grid reported. Obviously, these have to be set correctly when people set up their software, or this is going to be incorrect. So you are dependent on individuals setting up their software properly. This gives us a calculation of kilometers per watt. So spot Q is a measurement of the relative quality of a spot, or how good it is. The best way to think about it is the spot that was received over the greatest distance with the lowest power and the best signal to noise ratio. There is a formula for calculating this. You can look it up. I won't get into it here. But basically it gives you a way of ranking the quality of each spot and which spots were the best and which spots were the worst. And I was using version 2.12 of the WSJT-X software. So this is just reporting the version of software. So this is our receipt from things. We can also do things like look at a map. And I really like the mapping of this because it really gives me an idea of what it is we're seeing. So I'm going to zoom out a little bit more on this map. And we can see that, we were seeing some transmissions coming in from Europe during that time frame, probably on 17. Yeah, yellow is 17, so this one was on 17. There was some on 20 as we ran 20. It looks like I had one on 30 meters right here. So as I cursor over it, it shows me the from and to, how many miles it is. And then the color of the band is the color of the loop there, the arrow is the band that it was on. And here's a band count down here. So you get, and look at that, I got somebody from Australia. I was able to pick up somebody from Australia. Very good, on 30 meters. So this is what's happened in the last hour. And it gives me a nice map. I also have charts that I can select from. So if I look up here, I can say, give me a spot quality check. And this will give me distance and what the signal to noise ratio per watt is. And I can roll over that and it'll tell me which spot it is. I can get things like distance versus time of day, which is great for looking at what time of day is best to operate on. So when I ran this over 7 days, I had a 7-day average of this, and I'll show you that. I can also get things like frequency versus distance. So it shows me which bands I'm getting the better distance from. So again, all these are great statistical data points from your receive or your transmit side. Now, we just did receive in the demo, so all we're seeing here is what we've received. And part of what I was trying to understand is how well am I propagating and how well am I transmitting. So we'll talk about that a little bit more when I get to the experience part. So that's just a quick look at the WSPR.rocks reporting system and how it looks into the database. There's a lot more this will do. I'm going to get back into it a little bit more when I show you the data that I collected over 7 days doing the experiment. Let's talk a little bit about my shack and the antenna. My shack's pretty simple. It basically consists of an ICOM 7300 with an LDG AT200 tuner. And I have a MacBook Pro, an old MacBook Pro circa 2012 that I use for running the digital modes. And all that is connected to the compromised antenna. So the reason I've called this antenna highly compromised is for 5 reasons. The first one is location. I am located in the neighborhood near 840 and Arno Road called Falls Grove. And that neighborhood has hills quite a bit around it. My house sits on a hillside where the backyard is about 730 feet above sea level. And surrounding it is anywhere from 850 to 950 feet of peaks. So I sit a bit in a bowl, and that always had me concerned that I was basically going to radiate right into the hillsides. The second issue is our HOA restrictions. Obviously, with HOA restrictions, I can't put an antenna tower up. In fact, I'm not supposed to have an antenna up at all. So as I said before, I fooled the HOA a bit in that we installed a bocce court in our backyard because our family loves to play bocce. And at each end of the bocce court, I put a 10-foot pergola so that we had a nice shady spot to rest while we played bocce. All makes sense to the HOA, and it looks very nice. But in order to be able to light the bocce court, I need to have some wires strung between the 2 pergolas so that we can see what we're playing on a nice warm summer night in Middle Tennessee. And obviously, if I'm going to put some wires across the bocce court, I might as well put an antenna wire across there. Now, the problem with that is this all sits on the hillside, as you can see. And so I'm only about 10 feet above ground with this antenna. And if you go to the horizontal plane to the southeast, it's only about 20 feet before it hits ground level again. And if you go the horizontal plane to the northwest, it actually slopes down even further, and the antenna, ends up being about 16 to 17 feet off the ground. And that is the third compromise with this antenna, the height above ground. mostly because it is not high enough. It should be, quite a bit higher. And it quickly starts radiating into the ground because it is placed on the side of the hill with minimal height. So that's the third compromise. The fourth compromise is the radials. Because of the bocce court and that I installed this antenna after the bocce court was put in place, so the radials only go around about 2/3 of the way, and they do bend at an angle up the hill and down the hill. So the radials are at an angle to the antenna, and not in parallel with the antenna, and they do run up the hill. So at some point in time, the actual end of some of the radials are higher than the antenna. The ends are at a higher height than the antenna height. And that's another compromise. I did make the radials of varying lengths in order to resonate at 80, 40, and 20. I think I actually went all the way down to 10 with the radial links. So I did have multiple radial links in there, but I don't have many radials. I think I only have 16 radials in total. So there aren't as many as would be a best practice. The last compromise is tuning. I put the antenna up based on a length for 80 meters. And when I looked at my antenna analyzer, I was able to see that I was not quite reaching 80 meters after all. Without the tuner and just with the raw antenna analyzer, I was short of 80 meters. So I needed to lengthen it a bit. And I did lengthen it about 10 feet. And retuned it, or checked the analyzer again in the tuning, and I was good at the very, very base of 80 meters. So I decided to add another length and see if I could move it at least up into the digital modes, the band for the digital modes, and was not able to do that. So I ended up with 2 splices in the antenna. And of course, since this was a temporary experiment, I did not, do great splices, and I've left them in the weather. So that's the last compromise, is that the antenna does have 2 splices in it in order to get the lower end of 80 meters to tune up. Knowing all those compromises, I wanted to come up with an experiment so that I could understand how well this particular antenna works against other antennas that I might install. So the experiment that I decided on was I would use Whisper for 7 days straight, transmitting at 10 watts. And I would transmit on 40, 30, 20, and 17 meters. I transmitted at a 15% transmission interval, which comes out to 4.5 times per hour, or 108 times per day. So I did that for 7 days. And the last thing was to make sure I collected the data in a way that I could compare it against future antenna installations. So using the WSPR.net database to collect the data, and WSPR.rocks website to basically pull the data off and store it, I'm able to actually add that data, pull that data up in the future, and look at it against current data on a separate antenna. So that's the reason for the experiment. And now what I'd like to do is show you what the results were of the first round of this experiment, which was analyzing this compromised long wire antenna. Just taking a look at some of the statistics in the data, I had 17,132 reported receptions of my transmission in that 17-day period. Now, some of those were duplicates. They heard my signal multiple times on the same band, and in some cases it was the same reception call sign that heard me on multiple bands. So some of these are duplicate sites, but I wanted to keep all the data together, so I've kept all the duplicates in the data. There was 1,098 unique reporting stations, so of that 17,000, 1,098 were unique. The furthest was VK6PK, which is in Perth, Australia. So that was 17,800 kilometers. And the closest was right here in Brentwood, N4AAA, 20 kilometers away from me in Brentwood. So that's some of the high-level statistics. We're going to move into the WSPR.rocks website now, and I'm going to pull up the data from the 7-day experiment, and we'll take a look at some of the statistical analysis that's available both in the mapping and in the charts that they provide. The first thing I'm going to do is I'm going to call up the data set that I had saved off after I finished my 7-day period. So within WSPR.rocks, you have the ability to save off your data that you queried in either a table format that stays within the web browser, or export it as a JSON or comma delimited text file. And so I'm going to call that up now. I'm going to go to the table, and I'm going to look at table options. I'm going to load a stored table here. So you can see I've got a table here that I've stored. I stored it on 26th of April, and it was the end of my test period with my unique only spots. So this will be a table of the unique spots, which there is 1,080 spots. So that matches what I had as my unique number of spots. And what I want to do is just kind of take a look at this data now and see what types of information I'm able to pull out of it. The first thing I really want to look at is how far away we received some of our spots. So here is the spot in Perth, Australia, VK6PK. And if I click on the call, it'll tell me which country it is here in the red. You can see that it was 17,842 kilometers away, which is great because the signal to noise ratio was -20. So it wasn't the worst signal to noise ratio. You can see I've got here some at 32 and 33. And if I search on or sort on signal to noise ratio, -32 was the worst signal to noise ratio spot that we had. And that was also in Australia. So going back to spot Q, the spot in Perth, Australia was the highest spot Q, mostly because of the distance. The worst spot Q was actually something that was only 20 kilometers away, N4AAA, and that's in Brentwood, Tennessee. What this is telling me is that the concern I had with the hills and the propagation of my antenna out of this bowl that I'm currently in was not something to be too concerned about. It only really seems to be affecting the local spots, or the local QTHs. So, the local one had a -24 signal to noise ratio, which is not that much different than what we were seeing in Australia. However, the distance was only 20 kilometers, so it should have been a lot stronger than that. So those hills are actually creating some level of attenuation of my signal. There's no doubt about that. But I'm getting up and over them and skipping over the atmosphere and getting all the way to Perth, Australia. So that is good, and that's what I want. Another thing we can do here is take a look at the map. The map, again, is one of my favorite things. So this is my 1,080 unique contacts over a 7-day period on a map. And down here I can see the contacts I've made on 40, 30, 20, 17, and 15 meters. I only had one contact at 15 meters, which I find interesting that there was only one. You can click on these and see the individual ones. So there's all the 40-meter contacts, of which I was able to get both Australia, Europe, and South America. Here are the 30-meter contacts, which was even more significant for Australia and Europe. So 30-meter was definitely a little bit stronger, it appears, for me. The 20-meter contacts start limiting things down to North America only, a few Europe and a few South America. 17 meters, obviously, that becomes even closer, though I did have one here in Colombia and one in Hawaii, so that's good. And then the 15-meter one, I had a single contact here in Naples, Florida, WC6X. The other thing, again, I can do here is I can look at an animation or basically visualize what the contacts are, the spots are, over the time of day. So by sliding this arrow button here, you can see the gray line moving across and where the contacts were happening and where they weren't happening during the 24-hour period. Now, this is an average of all 7 days, or not an average, but a total of all 7 days. The next thing I'm going to look at are the charts. There's a number of charts here that I think are valuable. First one is spot quality. It gives you a way of visualizing the spot quality, that spot Q component that we were looking at earlier. Here you can see way out at 18,000 miles is our friend in Perth, Australia. If you look at this in the groupings, we basically got the North American grouping here. We've got the South American grouping here. Here's our European grouping, and here's our Oceanic grouping. So we can see kind of where we are getting and which bands. The bands are color-coded, the same color coding that we were seeing before. So looking at 40 meters, there is 30 meters, so forth and so on. The other chart that is good to look at is signal-to-noise ratio versus distance. So this gives me an idea of how my signal-to-noise ratio is applying across distance. It's interesting that as I look in some of these worst-case signal-to-noise ratios, they are very near to me. Some are just a few kilometers away, and so obviously, like we were talking about before, the hills and the propagation out of this bowl is really significantly a problem for the people who are closest to me, and the stations that are further away will have less problem. So the problem that I was having with the concern I was having with the hills is something not to worry about. Let's take a look at SNR versus time of day. Signal noise ratio versus time of day. We're getting a pretty good scatter here. This is something that appears there's no really good grouping. You can see an average line here is being created. So, we have the worst signal to noise ratio in the early morning. It seems to get a little bit better towards noon and then a little bit worse in the afternoon. So, whether or not this is representative of things over a longer period of time, I don't know, but it gives me at least something to look at with this particular antenna on those particular days. Frequency versus distance is nice because I can see which bands I'm getting the best results on from a distance. No surprises here as we go into the lower frequencies. We get a little better skip and a little better distance. So 40 meters gave me the best results, and 30 and then 20. And here's my little 15 meter guy all the way up here from Naples, Florida. So, this is the frequency that we had versus the distance that we accomplished with that spot. So to provide a conclusion to this experiment, the main thing is that WSPR provides a lot of great data, and the tools provide you a way of visualizing that data that can really help understand how your antenna is working and how propagation is happening around the world. And although this particular antenna, this long wire antenna that I have installed now, is compromised in a lot of ways, it works, and I do make contacts around the world. And I should be able to continue doing that with other modes, including voice and CW. It's probably worth an investment for me to improve this, especially improving the radials and the extensions, taking those extensions out and putting a single cable or single wire all the way across. And I'll be doing that this summer. The data that I've gathered is going to be very useful as I look at other antenna installations. So I will probably this summer also install a off-center fed Wyndham that is set for 80 meters. And I'm going to do that from the very top of my chimney down to each side of the pergolas. That will give me a inverted V sloper with a off-center fed Wyndham at 80 meters and cover quite a few bands. I'm hoping to see that that's a big improvement. I did a very similar temporary setup for Winter Field Day using that antenna, the OCF antenna, and had pretty good results on voice and on RTTY. The last thing that I really enjoyed about doing this experience is that I can actually play ham radios while I'm sleeping. I can turn on this Whisper program and set it up to run 4 or 5 days and not worry about it. So it was nice to come down and look at the data every once in a while as it was being collected and let the radio just do its automatic sequencing. So that's my presentation on Whisper and the experiment I did with my compromised antenna. Look forward to talking about this more and getting any questions from you.